For the video presentation, I chose problem 10.6 from the textbook, and this is the problem statement pasted, and this is the table 10.20, which has the time of day and the intensity and the flow. So part A asks for the average infiltration capacity, and to determine that you need peak flow and inflection point, which you can see on this graph. The peak flow is up here, and then this is the inflection point at 10 a.m. And those corresponding flow rates are 3.812 meters cubed per second for peak flow and 2.476 meters cubed per second for inflection point. And from those points, you can determine the base flow as well as runoff. And for the base flow, you assume that all of the flows up until the peak flow are the lowest, 0.009 meters cubed per second. And so you have to plug it into this equation for infiltration capacity, which is rainfall minus runoff volume divided by area, and then you also have to divide by the time. So the rainfall volume is 34,465 meters cubed, and the runoff volume is 5,362 meters cubed. And you divide by the area, which is 121 times 10 to the fourth meters cubed. And then you have to multiply by 1,000 as unit conversion, and then also 60 minutes as a unit conversion. And I got the 38 minutes from this table right here. 8:57 to 9:35 is 38 minutes. And the infiltration capacity is 38 millimeters per hour. However, you have to adjust infiltration for the times when the actual infiltration is less than the infiltration capacity. So the actual infiltration capacity is 75 millimeters per hour, because if you the equation will yield the same runoff volume. And the soil is class A. Part B of this problem asks for the average curve number. So you'll use this equation to determine P, which is rainfall depth, and that's the total rainfall in volume divided by the area. And after some unit conversions, you'll get 28.5 millimeters. And then you have to determine Q, which is the runoff depth, and you'll do the runoff volume divided by the area. And after some unit conversions, you'll get 4.43 millimeters. And then you'll plug it into this equation. Q is equal to P minus 0.2S squared divided by P plus 0.8S. And if you plug into the calculator using number solver, you'll get S is equal to 44.92 millimeters. And then you'll plug S into this curve number equation, and then you'll get a curve number of about 85. Part C of this problem asks for the time concentration. So you'll use this equation and find the centroid of rainfall, and using that equation you'll get that the centroid of the rainfall excess is about 17.9 minutes, and then you'll use that and plug it into this equation to solve for TC. And I use 44 minutes because the peak runoff is at 9:46 a.m. and the time starts at 9:02 a.m. so that's a difference of 44 minutes. And I got a concentration time of 43.5 minutes. Lastly, this problem calls for practical uses of these parameters, and so I think that you can use these parameters in determining if losses are primarily from soil infiltration, and you can also use it as a model experiment. If you're wondering the same things as this problem statement did, you can follow this problem to determine if losses are primarily by soil infiltration.